Okay, so thank you very much for the invitation. It is a pleasure to give this talk, and even if I would prefer to have given it at ICTS. So this talk will be about some old subject, which is so the main topic is to understand in some quite classical and new models the localization effects and transport properties in chains of oscillators. So in fact, my talk will be divided in two parts, which are quite independent. And so if you are not able to follow for the first part, you can go to the second part, and it will be almost, there will not be some, okay, you can skip the first part and go directly to the second part. It will not be a problem to understand. So, but they are related in the sense that they are discussing some similar problems, which is the effect of the randomness in a harmonic chain of oscillators, and the effect on the transport properties of his randomness. So, in the first part, which is based on some work with François Huveners and Stefano Avolla, I will discuss the hydrodynamic limits for a chains of harmonic oscillators with random masses. And in the second part of the talk, which is some joint work with Junet Bat, which is a PhD student of Abhishek, Gaetan Khan, my own student, and Abhishek, I will discuss problems of, I will introduce some a new model of harmonic oscillators with random charges in presence of a magnetic field. I will study the localization effect on the transport properties in this model. So let me start with the first part. So I will, so it is a chains of oscillator with random masses. And so the model is the following. So just a classical model, you have some harmonic chain of oscillators. So here you have n+1 oscillators with some interactions, which are just harmonic interaction. So here you have it is one-dimensional, very important one-dimensional lattice. On this lattice you have particle I +1, and so on. And I call Mi the mass of the particle I. Pi is just the momentum of the particle I, and Qi is the displacement of the particle I from its equilibrium position I. Okay, so I call it position of particle I, but it is in fact just the displacement with respect to the equilibrium position. And I will introduce, in fact, it is simpler to write the dynamics, which is classical dynamics, in terms of the interdistance particle. So Ri, which is just different between the position at I+1 minus the position at I. And then, so the dynamic is very simple. It's just given by the Newton's equation with some potential, which is just a quadratic potential. Okay, the derivative of the velocity is, okay, sorry, here, what I wrote here, okay, here, okay, it's a big mistake here. Okay, you understand, it is a derivative of Ri, which is just Pi +1 minus Pi, sorry, this is false. Okay, just a Newton equation for chains of oscillators. So sorry if this equation is false. And it is Ri dot, it's just a Pi +1 minus Pi. And here it is, okay, and here it is false also, okay, oh my God. I mixed the R and the P. Okay, but you know what I mean. I don't know, okay, no, everything is correct, sorry. Sorry. No, everything is correct. The derivative of the, okay, the derivative of the momentum is just, okay, it is harmonic forces. And here just the derivative of Ri, just velocity I +1 minus velocity I. Okay, no, everything is okay. And now I have to impose some boundary conditions. And so I will discuss mainly in this talk fixed boundary conditions, which means that I assume that here the particle 0 is just fixed as well as the particle n+1. Or free boundary condition. So in this case, it means that here the two particles are, in fact, it is not a spring which can move, but it is a fixed spring with a length which is fixed equal to 0. So this is the dynamics, very simple dynamics. with Harmonic chains of oscillators. Of course, it is not a new model. It is a very old model, which has been studied during many years, since a very, very long time. And so this system has, of course, three physical conserved quantities, at least in the bulk. Maybe because of the boundary conditions, they are not exactly conserved, but in the bulk, they are conserved three important quantities, which is the energy, okay, the sum of the kinetic energy plus the interaction energy. So I decided, just a convention, I decided to put all the energy of the interaction between I and I plus 1 to the particle I. So if you want, you can replace here Ri squared divided by 2 by Ri minus 1 squared divided by 4 plus Ri squared divided by 4. But it will not change nothing at the end because you take the sum. And the momentum is also conserved, and also some quantity, which is called the stretch or elongation of the chain, which is also conserved. And of course, they are not the only conserved quantities of the dynamics, because this dynamics is completely integrable. And if you introduce the normal modes of the chain, which are the solution here of this equation with omega k, which is dispersion relation, and minus delta is the discrete Laplacian, n is the matrix, diagonal matrix of the masses of the chain. Then you introduce this psi k, which are some function of r and p, which satisfies this orthogonality condition as the bracket of psi j. And so it is a bracket which is perturbed by this diagonal matrix. Then they are orthogonal with respect to this scalar product. And so the dynamics is completely integrable because the energy of each normal mode is in fact equal to 0. So it is like if you have some modes which are independent and not interacting with phonons. And so it means in particular that you have some set of integrable conserved quantities which are given by the sum of all these energies of each phonon. So, but these one are the three usual conserved quantities in chains of oscillators, and we expect that when you introduce some non-linearity, they will be the only one which will survive. Of course, it is not totally true because, for example, if you consider some exponential potential, you get the total lattice. And in this case, we know that this is still some integrable dynamics. So it happens that for some special non-linear potential, non-quadratic potential, sorry, for non-linear interactions, maybe you have more than only these three conserved quantities, but we expect that in general, for generic potential, interaction potential, you have only these three ones. And then associated to these three conserved quantities, so you can introduce the standard Gibbs ensembles, which are just given by the following expression here. So here beta is the inverse of the temperature. You have the average momentum, the average velocity. So you have to think a bit because here we have several masses, different masses. So I introduce this notation here with, oh, sorry, it is mi here, and m bar is just the average of the mi. And here it is the average stretch of the in this standard Gibbs ensemble. And of course, since the dynamic is integrable, in fact, it is not the only invariant measures of the dynamics, because more generally, since you have some set of integrable system, we have a generalized Gibbs ensembles for which the standard Gibbs ensemble is just a particular example. And these generalized Gibbs ensembles are just given by the following expression, where here, instead of putting the three conserved quantities here, in fact, if you develop this square, you can express it as some coefficient, exponential of some coefficient chemical potential in beta in front of the energy, plus some other parameter in front of the pi and some other parameter in front of the Ri when you expand this guy. But more generally, you can construct some set of conserved quantities, which are not this one, but which are conserved quantities, which can be expressed as a sum of the translation of some local quantities. And then you can introduce this, what is called in the Doyon-Spohn theory, the generalized Gibbs ensembles. And for which these ones are just particular case. Okay, So this is the model I will be interested in this first part of this talk. And so what what we would like to do, it is a standard question, is the obtention of the hydrodynamic limit in the hyperbolic time scale for these chains of oscillators. So let me start with a basic example that everybody knows, which is the case where you have only some all the masses of the oscillators are the same. So if the dynamics was ergodic, which is completely false, what we would expect that if you start in a local standard Gibbs ensemble. So local means what? Means that it is almost a form of a Gibbs ensemble, but you let the temperature, the inverse of the temperature, the average momentum and the average stretch slowly varying respect to n. So it means that for particle I and particle I+1, for example, the temperature, locally the temperature is beta I over n or beta I+1 over n, so they are almost the same. Okay, so it is a local standard Gibbs ensemble. And so the general theory of statistical mechanics say that, okay, if you start with some local Gibbs ensemble like this one, we would expect that at time Tn, so in the hyperbolic time scale, so n is the length of the chain, the true state of the dynamics at time Tn should be close, in some sense to precise, to a local standard Gibbs ensemble, so some local Gibbs ensemble in this form, but with some new parameters, inverse temperature beta t, depending on the time t, some average momentum pt, and some average stretch rt, which are solution of some earlier equations. So this, it is what we expect, in particular in the case where you have some nonlinear potential, if the dynamics is not completely integrable. And of course, it will not be true for the harmonic chain here with constant masses. But if you do as if it was true, then you will get these earlier equations. Okay, here there are some special boundary conditions because we started with the fixed boundary conditions. No, sorry, free boundary conditions. And so this is the form of the equations that you will obtain here. M is just the mass of the system. And you see it is some pattern. Okay, it is nonlinear, in fact, because here you have the product of R and P, but it is falsely nonlinear because the evolution of the energy is just given by the evolution of R and P, where R and P is just the solution of the wave equation. And okay, so in particular, this earlier equation doesn't develop any shocks. So if you start with some smooth initial condition, at time t, you will get some smooth initial conditions. There is no dissipation and so on. And okay, of course, you can say, okay, that is false. We know that it is not true that the hydrodynamic limits for the harmonic chain with constant masses is given by that. But you observe something that, I don't know if it was observed in the past, but if you look at this equation, and if you look at the temperature profile, Tt, which is just the difference between the energy and the mechanical energy, then you observe that by solving this equation that this is equal to 0. So the temperature is not evolving with time for this earlier equation. And in particular, even if the dynamic is non-ergodic, this propagation of local equilibrium is usually false, but weaker forms may hold. For example, if you start with some local standard Gibbs ensemble, where the profile of a temperature here is just constant, doesn't depend in space. In this case, you can prove rigorously that these earlier equations are valid for this non-ergodic harmonic chain. Okay, it is, in fact, it is a weak form because we don't say that the true state is close to local standard Gibbs ensemble, with some constant temperature and some stretch and some new stretch depending on time, and new momentum depending on time. We just say that the average of the energy in the true state converges to the average of the energy in the local Gibbs ensemble. Okay, but it is interesting to notice that even in this very simple case, it is not because you have some dynamics which is completely integrable that you cannot obtain the standard equations that you will expect. So it is very different from the generalized hydrodynamic theory of Benjamin and Herbert, where what they claim is that in fact when you have some integrable dynamics, usually if this property that I mentioned here is false, and what they say, okay, but it becomes true if you replace the local standard Gibbs ensemble here by local GGE, local generalized Gibbs ensemble. And in this case, you don't obtain just a set of three conservation laws, but some continuous set of Euler equations. And but this example show in particular that, and maybe it is some question, I don't know, for people working in this theory, which is, okay, here in this example, we can see that there exists some special local GGE ensembles, which in fact are giving the standard Euler equation. Okay, it is just for the harmonic chain. I don't know if, for example, if you start with the Toda lattice, so we have so in some paper of Herbert, there's the generalized hydrodynamics for the Toda lattice, but maybe there exists some special initial local GGE, which are in some sense preserved and give at the end some set of Euler equations, which is not a continuum of Euler equations. Okay, so it is a question that I was asking to myself by preparing this talk. And so now I come to the main theorem that I wanted to present here, which is the validity, in fact, of the hydrodynamic limit in hyperbolic timescale for a disordered chain. So here now I assume that you have masses which are IID, identically independent, identically distributed random variables. And now, so I said before, remember that I say, okay, the propagation of local equilibrium for the harmonic chain, ordered harmonic chain, is usually false, but it becomes true, for example, if you start with a local SGE, standard Gibbs ensemble, where the temperature is constant, not depending on space. And here, what we proved with François and Stefano is that if you start with some local SGE in this form, where now we allow the dependence of the temperature. And we have some initial profile of the inverse profile of temperature, some profile, macroscopic profile here, P of a momentum, and some macroscopic profile of a stretch profile. Then there is some validity of the Euler equation in the hyperbolic timescale in the following sense. So in the sense that if you compute, so you have to take some test function f, but what here we say is that mainly that this average in the true state of the stretch in the true state at time tn is the same as the expectation that you will compute in some new local SGE with some profile beta, P, and R solving the Euler equations. Okay, and the same for the momentum and for the energy. So it proves that even if we have some non-ergodic dynamics, integrable dynamics, we have still the validity of the Euler equations. And so the Euler equation here appears as the masses of the expectation of the random mass. So n bar is the expectation of the random masses mi, and so they are exactly in the same form as the ordered chain, where just you replace here the mass, which was here before here, you replace it by the average. Okay. And we prove that. So it is a rigorous result. And so what is the idea and why it's working? Of course, it is very particular to the fact that we are working with the harmonic chain with random masses. So the idea is the following. So we know that now that we introduce some randomness in the chain, we have that the Eigen Modes. So Eigen Modes were just the solution of this equation, which is written here, with here omega k, which is dispersion relation. These Eigen Modes are localized now. Before they were delocalized, they are just some sine function mainly. But now they are localized, but in fact, the localization lengths psi k depend on the wave number k, and it starts to diverge when k is too small. So more exactly, the localization length is of order k over n squared, the inverse of the localization length. Okay, so it means what? It means that if k is very big with respect to square root of n, the normal modes are localized. And so if they are localized, they don't move, and so they don't transport edge. But for k less than square root of n, they are extended, in fact, and they are very similar, very close to the normal modes of the ordered chain. So you can split your normal modes in two parts, the normal modes which are localized for large wave number, and the normal modes with low wave number, which are delocalized and which are similar to the normal modes of the ordered chain. And if you start with some local SGE in the form I described here, and if you rewrite it in terms of the normal modes, what you observe is that the local SGE gives weight only to modes with small wave number, to the modes which are delocalized and which are similar to the normal modes of the ordered chain. And since, in fact, the normal modes with large wave numbers are not moving and not transporting energy, are localized, so it happens like everything happens like if you have some disordered harmonic chain in which you can replace just is similar to an ordered harmonic chain, but without normal modes with large wave number. And so if you try now to derive the equation with this assumption, you cut all the large wave number, then it is not so difficult to see that you will get the Euler equation, since the dynamics is completely explicit. Okay, the dynamics is completely explicit, which is what is not totally explicit is that psi k, in fact, depends are not fully explicit, they are just solution of some linear equation. But if you prove also that they are close to the normal modes of the ordered chain, then they become completely explicit, and then you can compute explicitly the dynamics with this assumption, and then show the validity of the Euler equations. Okay, so it is because of these localization effects that you can produce the validity of the Euler equations that you didn't have in the case of the ordered harmonic chain. And so I think this is an interesting remark that, in fact, often we say, if we don't have some sufficiently ergodicity in the dynamics, we cannot prove the validity of the hydrodynamic limits. And this example show that it is not true, this assumption. In this particular case, it is a particular case, we show that the validity of the hydrodynamic equation holds. So let me comment a bit on this result before to pass to the second part of my talk. So in fact, the Euler equations even for nonlinear chains can be obtained rigorously before the shocks, before the presence of the shock, for an ordered harmonic chain, but also for some ordered non-harmonic chain, anharmonic chain, by restoring artificially some ergodicity. So, for example, you have just to add some energy and momentum to the energy momentum conservative stochastic noise. So you don't destroy the conservation of the conserved quantity, physical conserved quantity, but you restore artificially some ergodicity. And then by some techniques due to Jaon, Varen, you can prove the validity of his Euler equations. And but when you look at the proof, in fact, of his thing, so the basic mechanism is the same as the ones that we have for the disordered harmonic chain. By introducing this energy momentum conservative stochastic noise, what you do is that you cut or you destroy the high modes of the harmonic chain. Okay, but you preserve the low modes of the harmonic chain, in particular the momentum. And it is a reason for which you can derive the Euler equations. So it means that basically it is the same process in order to obtain these hydronic limits and the reason for which it works. And okay, but hydronic limits give just a typical evolution of the empirical conserved quantities. Okay, which is exactly what is here. You see, it is just some, mainly it is a law of large number for the empirical stretch, empirical momentum, and empirical energy. And so a natural equation is what is the form of the fluctuations? What is of the fluctuations of the energy, for example, for some disordered harmonic chain? In the case of ordered harmonic chain plus energy momentum conservative noise, for which the Euler equations, okay, here it is ordered, okay, and the energy conservative noise. So in this case, we know that the hydronic equations are given by the Euler equations that I presented before by phase 1, okay, and then you can start to study the fluctuations for this system. And what you observe is that you have some superdiffusion of energy, which is driven by a fractional Laplacian of order 3/4. So it was proved in this paper by Milton Jara and Thomas Komorowski and Stefano in a few years ago. And so a natural question is it true that this also happens in the case of the disordered harmonic chain? Are the fluctuations also given by some fractional Laplacian of order 3/4, or is it something different? Okay, because the Euler equations are the same, and the mechanism is almost the same. So the noise here in the case of the ordered harmonic chain was destroying the high modes, and in the case where you have random masses, it is also the destruction of the high modes. And okay, let us mention also there is some paper by Amir Ali Anani, which prove exactly the same result as the things that we proved here. In the case where you consider the quantum version of the disordered harmonic chain. So in this case, it is more difficult because the local Gibbs state don't have this special here product form. So in the quantum case, you have more correlations to control, but at the end, it's also work in some quantum context. Okay, good. So now I will pass to the second part of my talk. Since I think it's okay, yeah. I will discuss some joint work with Junaid, Gaetan, Abhishek, and which concerns some new models, because the models I presented before was a lot studied during the 70s and probably before. It is a chance of oscillators with random charges in the presence of a magnetic field. So let me just so come back just briefly to some genesis. So a different setting to study transport of energy is to consider the chain, the harmonic chain, in contact at the extremities with some thermal lunge and bath at different temperature at the boundaries. So TR on the right, TL on the left, And then since the temperature are different, you have some in the non-equilibrium stationary state, you have some heat current going from the hottest reservoir to the coldest reservoir. And this heat current, in the non-equilibrium stationary state, the average in non-equilibrium stationary state that I denote by Gn, okay. So the question is, a typical question, which is standard in this field, is what is the scaling respect to the length of the chain of this heat current in the NES as n goes to infinity. And in particular, it means that if you have Fourier's law, it means that this average current should scale like n minus 1, because, okay. So if you don't have this scaling, it means that you don't have Fourier's law. And so, of course, as we know that in the case where you have some ordered chain with masses all constant equal to the same value, then the transport is ballistic, which means that Jn, the average current scale like just of order 1, so it doesn't goes to 0 like 1 over n. And this was proved a long time ago by Reader Leibowitz, but it was known since a very long time, in fact, in physics. And for the disordered chain, okay, what we have said is that due to the Anderson localization effect that I described before, some modes, the high modes are blocked, are localized, but the low modes are not localized, so they still transport some energy. And consequently, what you have is that, in fact, okay, then you have some very high sensibilities to boundary conditions, and in particular, you get the following scaling. Gn is 1 over square root of n for free boundary conditions, and Gn is equal 1 over n3 alpha for fixed boundary condition. So in case you see, it means that here you have some super diffusive behavior, because you have, in fact, if you multiply by n, the average is it is of order square root of n, but here if you multiply by n, it is just 1 over square root of n, so it goes to 0, so you don't have any transport of energy. So it is very sensitive in this case of the boundary condition. Okay, there is a huge literature about this problem. It was studied a lot during the 70s, and it came back to a rigorous proof by François Venez in around 2000. And okay, there are many other developments around these things. I didn't cite all the literature about it. And now I would like to introduce some new model, which is in fact, which was inspired by some paper by Keiji and Makiko Sasada. So it is some chain of oscillators, but now so it is only one-dimensional chain of oscillators, but each particle has 2 degrees of freedom. So each particle can move in this plane, which is represented here. So 2 degrees of freedom. So each particle is moving in this plane. And we assume that on each particle has a charge. And the charge can be different from one particle to the other particle. And we put this harmonic chain in a magnetic field, which is transverse to this plane. And we fix also some thermal reservoirs at the boundaries of the chain. And then we want to study the same basic question: what is the form of the heat current in this non-equilibrium stationary state, where we introduce this magnetic field? So if you want to have some equations, they are written here. So I told you that each particle has 2 degrees of freedom. So now you have not only one coordinate, but x and y. So x, y are the coordinates of the particle n. So they are interacting just by harmonic interaction. There is the effect of the magnetic field here, Bn. Bn is just a random charge times B. So the magnetic field, if you wish, is not the same from one particle to the other particles. And here you have the action of the thermal bath at the boundaries. And here there are the Cn. So the Cn here are basically 2, but depending on the boundary condition, I have to replace it by 1. If for free boundary condition, I have to replace this C1 by 1 and C capital N by 1. But mainly it is 2. okay, for free boundary condition, for example, for fixed boundary condition. Sorry. So Bn, so in the rest of the talk, I will mainly consider the case where Bn are IID random variables. Okay, so the magnetic field is random. So the dynamic is completely deterministic, and okay, here you have the lunch and bath with these temperature at the boundaries, corresponding to this temperature at the boundaries, TL and TR. And so you observe that dynamics is completely linear, so it can be solved more or less explicitly, but okay, depending on the normal modes of his chain. And the question is asymptotic of the average heat current GM in the nest for large n. Okay, so it turns out that we can compute. Here, okay. We can compute this average. We can get some expression of the average current by using some non-equivalent green function for formalism, which was introduced in Kasher-Leibowitz in 71, which was revisited by Abhishek and probably by other people and some collaborators during at the beginning of the century. And so by in fact, by using this non-equivalent green function, in fact, this system is very similar to the electron transport in superconducting wires, which was studied by Junaid and Abhishek very recently. And by this similarity, we can also get some expression of the average current, which is what? So the average current is proportional to the difference of the temperature at the boundaries, and multiplied by some interval over all the frequencies of the normal modes with some transmission coefficient Tn, depending on n, on the length of the chain. On this Tn, the transmission coefficient is explicit, quasi-explicit in fact. So gamma is just the strength of the reservoirs. So it depends of these two quantities, Fn plus and Fn minus. And what are Fn plus and Fn minus? They are given by this expression here, where small f and small g are in fact the solution of this recursive equation. Okay, and here is a Bn. I recall you, they are independent random variables, and the Cn mainly is 2. Okay, it is 2 in the bulk, and it is only at the boundaries. If you have fixed or free boundary condition, can be 1. Okay, but mainly it is 2. And so you see, if you want to understand what is the behavior of Gn as n goes to infinity, you have to understand what is the behavior of this transmission coefficient when n goes to infinity. And if you rewrite this equation, or recursive equation, you can rewrite them in the form of a product of matrices. Okay, if you, in fact, okay, yes, let me just say that before that, if you take the Bn constant, okay, so you have a magnetic field which is uniform, then you can compute everything explicitly here, and you obtain that the current is ballistic, like in the case of harmonic chain with ordered harmonic chain. You have ballistic transport. Now, if the Bn are random, with some variance which is strictly positive, then you have some Anderson localization effects, and which are can be seen, in fact, in this product of matrices, because you can rewrite this recursive equation in terms by forming the vector Fn plus 1, Gn plus 1. Like here, you see that you can express it in terms of these 2 by 2 matrices. And because these Bn are a random variable, then you have some localization effect which appears, but this localization effect will disappear when omega goes to 0, because the randomness is proportional to omega. So we introduce a Lyapunov exponent corresponding to this random matrix. We know that it exists, and that in fact is independent of the randomness. Here I put the average respect to the randomness of the magnetic field, but in fact you can remove this average, and this Lyapunov exponent exists. So okay, so this is the Lyapunov exponent corresponding to this equation. And basically, you see this Fn plus and Fn minus should be proportional to exponential n lambda of omega. So it means that if Tn of omega will be small, it will be exponential decaying with some decay given by lambda of omega. So as omega goes to 0, phase lambda of omega will go to 0. So only in phase interval, what will count is only the small frequencies. And more exactly, yes. Mainly, what will count in phase average current is the following. It is a small frequency. So in fact, we can introduce some cutoff of frequencies in terms of the Lyapunov exponent. So here, omega max n is just defined as the solution of this equation. And so we can cut it like that. And then we have to understand what is the limit of the transmission coefficient. And then, so you can look at the numerical simulation of the transmission coefficient. So here on the picture, it is a transmission coefficient when n is increasing, and for the constant magnetic field. So in the constant magnetic field, you see you don't have some, it is in log scale, okay, respect to the frequency. So it is like that. And if you look at the case where you introduce some randomness, you see that this transmission coefficient is going to 0 very fast when omega is far away from 0. And moreover, if you can suspect by looking around 0 that the picture which is here is very similar to the picture here. This is something which happens for the case of harmonic chain with random masses. Also, we have some expression which is similar like to this one, and you can prove rigorously that the transmission coefficient, the limit of this transmission coefficient, is the same as the transmission coefficient with masses which are where the transmission coefficient of the order chain with a mass equal to the average of the mass. So here we make the same assumption based on this graph. We say that the transmission coefficient can be approximated in the large limit by the transmission coefficient of the ordered chain, where the magnetic field is constant, but with a constant magnetic field equal to the average of B and with the corresponding boundary condition. And we have introduced this cutoff of the frequencies, okay, which is given by the Lyapunov exponent of this product of 2 by 2 matrices. And so the natural question is, what is the behavior of this lambda of omega, of this Lyapunov exponent for omega goes to 0? Okay, so I recall you that this lambda omega was defined here in terms of this product of 2 by 2 matrices. Okay, but it is just, you can also write it as a second order discrete equation. So we have first to understand what is the behavior of the Lyapunov exponent. And okay, and it is only for omega small, which is what is important. In fact, so you can linearize by considering only the first order in omega. So here you introduce the fluctuations around the average magnetic field. And here it is just the average of the magnetic field. Okay, so here now, if you want to understand the Lyapunov exponent of his expression is not so easy in the cases where B is the average of B is negative or less or equal to 0. So we expect that in the continuum limit, so we replace this equation by this stochastic differential equation by some not very well justified theoretical justified way. We replace it by this continuous equation. Okay, here you have the same term, and here you have just we replace this guy by some white noise, standard white noise, where sigma just variance, sigma squared is the variance of the magnetic field. And then we claim that this the Lyapunov exponent of this UN is the same as the Lyapunov exponent lambda star of his UT. And UT of omega, in fact, because of course depends on omega. And then here it is easier to study, in fact, very rigorously the Lyapunov exponent of his stochastic differential equation. And we obtain the following result, which is in fact based on some paper by Pichut and Pavu, some old paper, mathematical paper, but proof is quite easy in our case, in fact, by some standard computations. And we observe that there is a rich behavior of the Lyapunov exponent depending on omega, depending on the average of B. Okay, so in particular, the case where the average of B is equal to 0, we have some Lyapunov exponent, which is omega 2/3, while otherwise it is omega or omega 1/2. So here, this Lyapunov exponent doesn't depend on the boundary conditions. And we claim that lambda omega is approximately equal to lambda star omega, which is well justified numerically. We get some good agreement with this approximation, which is here, not only at the level of the exponent, which is here, but even the prefactor are very good, very well approximated. So we have the first ingredient. Now by using this result, we get this cutoff here, and if we make this assumption, we get just the transmission of the ordered chain, which is completely and explicitly computed. And then it is sufficient to give some prediction for the average current of Gn. And the average current Gn that we obtain is summarized in this table here. So you see there is still a difference between fixed and free boundary conditions. And also depending if you have some magnetic field which is different from 0 or some magnetic field which is equal to 0. And so here, the transmission coefficient of the ordered chain can be computed explicitly, and it's given by the following quantity, depending of all these boundary condition and value of the average of B, and the Lyapunov exponent, we have it, and we get this different behavior. So now we can compare with the numerics, and what we obtain in the numerics here, you see, you have very good agreement when you have some average of B, which is different from 0. So it is this guy here and this guy here. So in this case, we get some good agreement independently of the boundary conditions. So these exponents are different from some this coefficient in particular is different from the coefficient for the chain with random masses. But when we look at the case where the average of B is equal to 0, it is quite the numerics are not so good. In fact, you see there are some discrepancies here, and so we had some doubts about our predictions in the case where the average of B is equal to 0, and then we looked at the transmission coefficient, because to compute this average current, I use these assumptions here that this limit of the transmission coefficient, when you average over B over the realization of the magnetic field, it should be like the transmission coefficient of the ordered chain with a constant magnetic field equal to B. But we had some doubts that maybe this prediction was not well justified. So we did more accurate simulations. In fact, Gene did some very good numerics. And what we observed in the case where B is different from 0, it is in perfect agreement with his assumption. Okay, here it is a transmission coefficient, and here it is, so I don't know if you see very well, but it is a comparison between some uniform magnetic field, some disordered magnetic field for different boundary conditions, free and fixed boundary conditions. Now, if you look at the case where B is equal to 0, then we see that the assumption is not well justified because you have some difference here. So in the case where the average of B is equal to 0, probably the predictions which are here are not correct, because there is some discrepancies here that you observe, and even the peaks here which are present are not represented in the, even if here you could say, it is very, very good. In fact, the peaks are quite different. And so our predictions are given by phase ones, but for the case average of p is equal to 0, there is more investigation is necessary to have some definitive answer. So, okay, my time is over, but I just, this last slide. So maybe I can just take 1 minute to finish. It is, some conclusions and comments is about the transport properties for a chain of harmonic oscillators in the presence of a random magnetic field and a different form. Okay, sorry. The transport properties for a chain of harmonic oscillators in presence of random magnetic field are different from a harmonic chain with random masses. And we obtain theoretically the behavior of the Lyapunov exponent in the three regimes with good agreements with the numerics. So for the Lyapunov exponent, even the proof is not rigorous, it is clearly well justified. But in the case where the average of B is equal to 0, it seems false to approximate the average of the transmission coefficient of the chain with random magnetic field by a chain with zero magnetic field. And this model with a constant magnetic field and some energy momentum conserving noise has been investigated in some paper by Keiji and Makiko Sada and Ijetsuda. And here they obtained some interesting form of the fluctuations because they obtained some fractional Laplacian with exponent 5 or 6. In fact, you can obtain also some different exponents by putting some small magnetic field, which depends on the length of the chain, and you obtain all the range of exponents between 3/4 and 5/6. And so it remains, okay, from the mathematical point of view, it remains to establish rigorously everything which has be done here, and to understand also the case where the average of P is equal to 0. And related to the first part of my talk, it would be also interesting to establish, is it possible to establish hydrodynamic limits in hyperbolic timescale for a harmonic chain in the presence of random magnetic field without any noise, just the noise coming from the random magnetic field. Can we do it similar to what we did with François and Stefano? And a similar question to the question I mentioned in the first part of my talk: what is the form of the fluctuations? In this case, are they given by this Laplacian, fractional Laplacian with exponent 5/6? So it was my last talk. Thank you for your attention. So it's the end. Thank you very much.
Yes, thank you very much. Thank you very much for a very nice talk, very interesting. So now the session is open for questions and comments. The audience, if you have questions, raise your hand. So, okay, so Alessandra.
Yeah.
Yes.
Your microphone is muted.
It's mute.
Yeah. Alessandra, you have to.
Okay.
Hi.
Sorry for the technical problem. So I have a question, so maybe two. So first of all, when discussing the Lyapunov exponent, you managed you worked with the variance of Bn as finite. So I suppose you are assuming that your random variables are with a finite mean and variance too. Also variance. Do you confirm?
Yes, exactly. Yes, it's true that. Yes, I could imagine that we could take some magnetic field, very large magnetic field, which is not a finite variance, and so okay, I don't know what we will get.
Okay, and so this assumption is also in the case of the random masses. Do you confirm?
Yes, I don't know if there are some works in the case where you don't have finite variance for the chain with random masses. I don't think that somebody look at that. Maybe because it, yeah. Maybe Abhishek knows, but I think it has not been done.
Okay. And last question concerning the disorder. Can you go beyond the IID assumption? So is it so important, or can you relax and just consider some decay of correlations?
But for which part do you mean? If it is for the second part?
For the first or the second part, at least one part.
For the first part, if you have, maybe it is not so important, but okay, technically probably it is, there are some difficulties, but a priori it should not be so important.
Okay.
We didn't investigate this question because, yeah.
Okay, thanks.
Next, Abhishek.
Yeah, so I had a few questions. So one is, I mean, so for the hydrodynamics, I mean, if so, if one started from the GG equations, I mean, so it's in for the disordered case somehow from the GG equations you can derive this hydrodynamic, the Euler equations with just 3 fields, is it?
Oh, no, okay. So let me come back to what I said is that, I'm sorry. So here what we did is that we started with this special local SGE. Now, if you want, you could try to start with some local GGE, general GGE. So in this case, okay, I asked in fact the question to Herbert, and he told me that his theory that they developed with Benjamin needs that some translation invariance of the dynamics to be applied. And here you see, because of the masses, you can say it is not translation invariant, so you cannot apply. But after you wrote me that in an email, I was thinking that I don't understand, because in fact, you can always assume that MI, you can see them as dynamical variables. Okay, they are static variables, but you can say, but they are just some variables which are not moving. So I add the masses as some part of the dynamics. And in this case, you get some translation invariance. So I don't know, it is more a question for Herbert or.
So sorry if I intervene, but why this is not a particular GGE?
No, it is a particular GGE.
It is, okay. So in a way, it goes back in the general. It could be inside the general theory.
Yeah, no, but what I was saying, Herbert told me that it is, you cannot apply this theory of GGE if you don't have some translation dynamics.
Okay, yes.
But in fact, if you introduce the masses as some variables, the dynamics becomes translation invariant. If you see the masses as some variables.
I know, what do you mean by variables? Like
I'm like a PI, like RI. I say MI is also, instead.
Oh, do you give a dynamics to the masses also?
Yes, but okay, trivial dynamics, because they are not evolving in time. But then you get some translation invariance of the dynamics. So I don't really, now I say, maybe it is possible. I don't know, Herbert is maybe not here, but
okay.
No, okay.
And in your case, so even with the disordered case, so the temperature profile doesn't evolve at all, and you basically just have sound modes in the system, right?
Yeah. Yes. So the temperature, you see, because the equations here, the Euler equations are exactly the same as the Euler equation of the other chain, and then if you compute the derivative of the temperature is not moving with time. So it is true not only at the macroscopic level, but also at the microscopic level. In fact, in the microscopic level, you can decompose into you can introduce the temperature, which is just the thermal energy, which is the difference between the total energy and the mechanical energy. And then you can show that it doesn't evolve in time, microscopically.
Okay.
So it is very particular to these equations, yes.
Right. Okay. And the final question, I mean, so supposing, I mean, you have a system where you have both localized and extended states. For example, you can have this even in 1 dimensions, or let's say in 3 dimensions. Then what do you expect? I mean, the hydrodynamic equations.
Okay, so in this case, I don't know exactly, because in 3 dimensions, so for example, in 3 dimensions, so you have some threshold for the localization, no?
Yeah, so you have some set of localized states and some diffusive states, let's say.
Yes, so maybe you should expect some earlier equations in the earlier equations corresponding to the earlier equations that you expect. Maybe it is possible.
Okay.
Okay, mathematically, I think it is much more difficult because we need some ingredients in the form of the length of localization, which are probably not proved in higher dimensions. I mean, from the mathematical point of view, but otherwise, yes, probably it should be possible theoretically to derive Euler equations for the disordered harmonic chain in higher dimensions.
Okay. Okay, thanks.
Okay, so next, Aritra, please.
Yeah, you are mute.
It's mute.
Hi.
Hi.
Okay. Hi. So I think my questions were somewhat related to what Abhishek asked. Like, I'm a bit confused about what this average of mass is over. So this is over the initial ensemble.
What do you mean? This M bar, which is here?
Yeah. Yeah.
I just the average. Okay, you don't see it. Maybe it is just the average of the masses. So I started with some masses which are just IID. Independent, identically distributed random variables. So it's just the average of the masses.
And okay, so these are like okay. I mean, these are just with a finite mean and variance.
Yes.
Okay.
And the variance, yes, finite mean, and the variance, yes. I don't remember exactly what we needed for the masses. But something like that, yes.
Okay. And so and this, I mean, and the second question is that in the second part of the talk, like, why when you use the cutoff, which is this lambda max, is the omega max is proportional to 1 by lambda. What is how does one understand that?
Because you see here, if you look at these equations here, you see, okay, I went a bit fast, but you see if is Fn plus of omega here. Okay, basically, okay, when omega is small, you see it is similar to Fn plus, like this one. And this Fn plus, if you see it is a solution of this recursive equation, that if you introduce the vector Fn plus 1, it is exactly the product of these matrices. Fn plus 1 plus Fn plus, the vector Fn plus 1 Fn, is the product of these matrices. Okay. So it means that basically the norm of this Fn plus 1 plus behaves like exponential of lambda omega n. Okay, so it means that this guy is 1 over this guy is exponentially small in n with some prefactor which is given by lambda of omega. So here in this equation, you have some, in some sense here, you have some exponential of minus n lambda of omega. So you can cut everything for which n times lambda of omega is sufficiently large. So it is the reason for which we introduce this cutoff, which is given here.
Okay, thanks.
Okay, so next, Amirari.
Hi, Cedric. So
Hi.
I had a question about this assumption that you're making, and it's apparently wrong in the case that average of B is equal to 0. No, that's the limit of this transmission coefficient is equal to the transmission coefficient with the average of B.
Mm-hmm.
So
yes.
Do you have any conjecture or expectation? How does it behave in case where B equals 0? So do you expect that you get only a correction up to a fluctuation part of B? Because if you see that product of the matrices, probably when average of B is equal to 0, the average will vanish, but then you expect to just see the next order of only the fluctuations come in the transmission coefficient. Have you thought about this?
Yeah, maybe you are right. I don't know. Yes, I don't know. Maybe, yeah. Could be that just as fluctuations have to be taken into account and could give some correct answer. I don't know if Abhishek, you have some.
No, I mean, yeah, that's the possibility. I mean, the fluctuations, I mean, somehow give some effective field, I guess. I mean, but yeah, I don't have a concrete thought.
No. Okay. Thank you. Okay. Let me give just one or two small comments about the question of Abhishek. So if you see the proof of these random masses, as long as the number of extended states is of order n to the power alpha, where alpha is less than 1, you can prove the hydrodynamic limit. But as soon as you get n of order n extended states, then at least the proof doesn't work.
Yes. Mm-hmm.
I cannot comment if it's still true or not, but I know that the proof that we have doesn't work for O of n extended states.
Okay, so for if it's a finite fraction of extended states, then it doesn't work, right? Okay.
Yes.
Okay.
Thank you, sir.
Thanks.
Thanks.
Are there any other questions or comments? Can I ask one question? In the presence of magnetic field, the position of the particle is relevant to discuss everything. So do you have idea to get the hydrodynamics? Actually, the hydrodynamics is not described by stretch only, stretch and momentum and energy.
You mean there is also the pseudo momentum is also conserved, yeah?
Yes, but if we apply magnetic field, position of the particle is relevant because particle make circular motions, and the position itself is relevant. And
so position is. So it means you cannot introduce the stretch. It is what you are saying. The stretch is
you cannot remove position. That
okay,
so
maybe
it's difficult to derive hydrodynamics. I may be wrong, but do you have a comment about this? The question is whether can you derive hydrodynamics for the magnetic field?
In fact, it is some questions that I asked to Makiko, and she didn't know. And I don't know exactly. Yes, what are the, because now it is two-dimensional. So yeah, maybe yes, because yes, the difference is going to 0 very fast. Yes, if is even if you start with something which is non-zero, then it goes in very fast to 0. So average of the stretch. Is it correct?
Yeah, sorry, I don't know. Yeah.
Okay. I think the stretch is not conserved. There are two conserved quantities: that the momentum and the.
It is not the momentum. It is a pseudo momentum.
Pseudo momentum, yeah, but it's conserved.
Yes.
So there should be an equation for that, an equation for an energy. They both should be kind of super diffusive. So they will be coupled in some way. But that's
Yes,
not.
but the momentum is a function of the position, not only the stretch variable.
Well, but position are not, as you said, not really exist thermodynamically. I mean, we should see what are the equilibrium measures in the system. What are the parameters, the two parameters, and.
But I think that in fact, if you write you assume local equilibrium and you write the equation that you should get, they are not evolving in the time scale.
No. It shouldn't look like Euler equation because there's no ballistic transport here. So
what do you mean there is no ballistic transport? If you compute the average current in the non-equilibrium state, it is of order 1. So it means it is like the harmonic chain. There is some transport which is ballistic in this sense. If you put the system in contact with reservoirs.
Okay, there's the trivial part.
But I think that hydronic limits evolve only in some super diffusive time scale, not in the super ballistic. In higher time scales than the Euler time scale. In the Euler time scale, I think that the fields are not evolving.
In the Euler scaling, you shouldn't get any evolution.
No evolution, you mean?
Yeah, no evolution. Yeah,
Yes.
or be trivial in a way.
Yes.
And got the super diffusive scale. And super diffusive scale, you should see these two quantities evolving in some, maybe uncoupled or coupled. I don't know. Maybe Makiko's talk more about this.
I don't know.
So if it's time, so let me close the first talk. Let's thank Cedric again.
Okay, thank you.
Thank you.